Yesterday, we learned a little bit about radioactivity. We learned that radioactivity is a natural process. We learned that it's a spontaneous process, a random process whereby a nucleus decays. The nucleus changes. And it can happen by three mechanisms: alpha decay, beta decay, and gamma decay. Alpha decay occurs when you have a nucleus that's big, but that big nucleus has a lot of protons and a lot of neutrons, specifically, though, too many protons. As a result of too many protons, we have too big of a repulsive force. You guys remember that there was an electrostatic force, a Coulomb's law force, that acted between proton and proton. And because they're both positive, they're going to repel each other. They act to push the nucleus apart, to break it apart. The homewrecker force, that is. Okay, it's trying to break it all apart. Versus the strong nuclear force, which is an attractive force that acts between proton and proton, proton and neutron, neutron and neutron, between everything in the nucleus that keeps it together. If the electrostatic force is bigger than the strong nuclear force, and that's what's going to happen if you have too many protons, too big of a repulsive force, then the nucleus will break apart. And when it does, it's going to release this little chunk. It's kind of like we'll sacrifice this little chunk of ourselves in order for the greater good, in order to save the whole, almost. We're going to break off an alpha particle in hopes of making the remaining nucleus just a little bit more stable than it was before. The alpha particle consists of what? 4,2 alpha means what? 2 protons and 2 neutrons. What's something else that has 2 protons and 2 neutrons? A helium nucleus. You may see on your test this symbol, 4,2 alpha. You may see on your test 4,2 He, means exactly the same thing. Okay, on your diploma exam, they tend to use the alpha symbol as opposed to the He symbol, but I would say, maybe 2/3 of the time. They use both. Be prepared for both. Understand that we're not talking about 2 different things. It's exactly the same thing. You just may see it written 2 different ways. All right, beta decay. We have 2 types of beta emission. There's beta negative, which is a particle that looks like this. You got a nucleus that's unstable and it breaks off a little chunk. Not like the alpha particle, smaller. It's quite a bit smaller, in fact. But it breaks off a little chunk in an attempt to make it more stable. What's a beta particle the same thing as? 0 minus 1 is an electron. How can we have an electron ejected from a nucleus when we don't have any electrons in the nucleus? We'll deal with that in a second here, okay? What's the other kind of beta decay? Well, if we have beta minus, we also have beta plus. A beta positive particle is exactly the same thing as a positron. And the symbol for positron, be careful here, is 0 plus 1 E, not P. If it's a P, it's a proton. Plus 1 E means it's the antiparticle of an electron. All right, beta negative occurs when? What's the condition that happens when beta negative occurs? You got too many neutrons. Now, these too many neutrons don't result in some unbalanced force or some repulsive force that ends up being bigger than the attractive force. Rather, it results in an energetically unfavorable state. The nucleus isn't energetically stable. So it does something in order to try to make the nucleus energetically stable. If you've got too many neutrons, logically, you want to get rid of a neutron. But we can't just kick a neutron out of the nucleus easily. So what we're going to do is change a neutron. One neutron becomes, well, we want protons. We got too many neutrons relative to the number of protons. So let's change a neutron into a proton. But the only problem with that is that the law of conservation of charge is violated. We have neutral and now we have positive. So something else has got to be produced in this process here. What is it? An electron. That's where the electron comes from. We get an electron that leaves the nucleus because an electron was generated inside the nucleus as a result of this energetically unstable state where we had too many neutrons. Now, beta plus decay occurs when we have what? What's the condition there? Too many protons again. Now, too many protons here don't result in too big of a repulsive force. It gives us a different problem. Depending upon the number of protons, depending upon the ratio of protons to neutrons, and so on, we get a couple of different problems with having too many protons. In this case, too many protons results in a nucleus that's not energetically stable, just like we had with beta negative decay. But instead of converting a neutron to a proton, we want neutrons. We have too many protons now. So what we're going to do in this case, because we have too many of them, is convert a proton, change a proton into well, we got too many protons, we want more neutrons, so let's change it into a neutron. What else we got here? What else comes out of this as a result of this fancy thing that's going on? You get a positron. That's E plus. And again, the positron leaves the nucleus because positrons don't belong in the nucleus. Finally, gamma decay. We said yesterday, gamma decay is that process that's kind of a byproduct of something else that's already happened. Could be alpha decay, could be beta decay, could be some other process that we haven't learned about, where the nucleus is left in an excited state. Something's happened, the nucleus is excited, but it doesn't want to remain there. It wants to go back down to its normal boring state. So when it does that, it gives off a photon, and that photon would be a gamma ray photon. So it's we'll just say a byproduct of something else. Nucleus is excited, but to go back down to its regular, normal state, that nucleus is going to give off energy in the form of gamma rays. Answer this question for me real quickly before we move on to the columns that we established yesterday. There is one big difference between alpha, beta, and gamma. What is it? I mean, clearly alpha and beta are not the same thing, but they have something in common that gamma does not have in common with it. What am I looking for there? What's the difference? What's the biggest difference between alpha, beta, and gamma? Ready? Gamma is electromagnetic radiation. Okay, it's an electromagnetic ray. It's energy, whereas alpha and beta are not energy. They're things, right? They're physical particles, matter, antimatter, versus gamma, which is just energy. Now, they're all ionizing. They all ionize matter. They all turn atoms into ions, whether we're talking about alpha or gamma. But the makeup of them is substantially different. Three of these things are things, and one of these things are energy. All right, let's rank these in terms of ionizing potential. And let's rank them in terms of the ability to penetrate matter as well, the ability to go through things as well. Which one has the highest ionizing potential? Which one has the strongest ability to turn atoms into ions, Stefan? Good. Alpha particles. Alpha particles have a very high ionizing potential. Very high. The good news is, and that's the bad news for alpha particles. The good news is alpha particles have a very low penetrating power. Like literally, maybe it'll penetrate a sheet of paper, but if you hold up a piece of cardboard in front of you or half a dozen sheets of paper, it's going to shield you just fine from alpha particles. Now, gamma rays would have, I don't want to say a very low ionizing power. They don't. It's all relative. Gamma rays can be bad, but they have the lowest of the three ionizing potential. The lowest of the three. But on the flip side of it, their penetrating power is really, really high. Yeah. In fact, gamma rays can penetrate several centimeters of lead or concrete or some other dense material. Beta, they're the fence sitters, right? They're the ones that can't even decide whether to be positive or negative. They're in the middle for ionizing potential, a medium ionizing potential. They're in the middle as well for penetrating power. Can't decide which way to go. Can't decide whether to penetrate matter really well or not, Okay, we'll sit in the middle. Can't decide whether to ionize atoms really well or not. Okay, we'll just kind of sit in the middle there. Jesse, question? So look at this example question. It says when a neutral, we'll just do this one together. Don't worry about pulling out your stuff for this. It says when a neutral meson particle decays, it produces an electron. In this process, it most likely produces what as well? What's a meson particle? Well, have you ever heard of that before?
No,
Have we ever learned about it?
no,
Does it really matter what it's called then?
no.
No. Yeah, you can trust me on that. Always. We've talked about that a dozen times, right? If you don't know what it is, if you don't know what it is because you just haven't studied, then all right, too bad. But if you don't know what it is because you haven't learned it in Physics 30, it doesn't matter. I promise. Now, we know that this particle is neutral. That matters. We've learned about what neutral is. We haven't learned about meson particles. Who cares what it's called? We have something that's neutral, and it produces something that's negative. Is that possible just to produce a negative from that? No, Sadie? How come? Good. It doesn't work with the law of conservation of charge. So we have to maintain the law of conservation of charge. Therefore, what else would be produced there? Something that's positive. What positive particle would be produced? We don't know, right? We don't know because we don't know what a meson particle is, right? But we do know that it's going to be positive, whatever it is that's produced there, right? So that's not directly what you saw back here, but it's an application of what we saw back here, right? Because we learned about this whole conservation of charge thing when the neutron and the proton were converted to other things. Same idea, exactly the same idea right here, except it's not exactly the same process. All right. Today, I want to go a little bit further with radioactivity and talk about transmutation. Now, I'm going to uncover the definition for transmutation in just a second. And when you see that, you're going to think, well, wait a second, that's the same thing as radioactivity. Not exactly. Transmutation is the conversion of one element to another. Nuclear or radioactivity is the decay of a nucleus. What's the difference? It's a subtle difference, but it's a difference. Transmutation is the umbrella term. It's the bigger term. Transmutation includes anything that changes one element to the other, including radioactivity. Radioactivity is an example of transmutation. There are other examples of transmutation as well, like nuclear fission, like nuclear fusion, which we'll talk about in the coming days. The one that we've learned about is radioactivity, but it's not the only way to cause transmutation. It's not the only way that elements can change from one thing to another. What we're going to focus on today is writing nuclear equations. Nuclear equations are somewhat like chemical equations. If you're familiar with chemistry, you'll know that you write chemical equations to describe a reaction that's taking place. And you'll remember as well that you have to make sure you balance the number of elements on each side. If you have 6 oxygens on the left side, then you've got to have 6 oxygens on the right side. Or 3 hydrogens on the left side, you've got to have 3 hydrogens on the right side. It's similar to chemical equations, but it's different in that we're not balancing elements. Elements change now. In nuclear equations, elements change. Carbon might turn into nitrogen. You had carbon on the left side, you got no carbon on the right side. Elements change, but the mass numbers and the atomic numbers don't. And that's what we've got to pay attention to here when we're trying to write these nuclear equations. The mass number and the atomic number on both sides of the equation have to stay the same. Just like in chemistry, the number of each type of element has to stay the same. Best way for us to get this is to do a couple examples. I'm not going to make you write down the questions for these examples because in the end, the solutions to these questions, which I do want you to write down, pretty much just rephrase the question. Don't panic about writing down the questions. If you want to, go ahead, but please do write down the solutions to the questions. This one says, write the nuclear equation for the transmutation of radioactive isotope radium-226 undergoing alpha decay. In other words, radium is not stable. We have too many protons. In an effort to make it more stable, to reduce that repulsive force, we break off a chunk called an alpha particle. The alpha particle is released. What else do we got left? What do we have left after the alpha particle is released? Well, we start off with radium-226. In chemistry, we would call that the reactant, what we start with. In nuclear physics, we usually call it the parent nucleus. Having said that, I don't really care what you call it. If I refer to it as the parent nucleus, I just want you to know what I mean. It's what you start with. Then we're going to have an arrow, just like in a chemical equation. That arrow represents something's happening. The nucleus is decaying. What's it decaying into? Well, an alpha particle. It produces an alpha particle, or you could write 42He if you wanted. Be careful to write the alpha particle on the right-hand side, not the left-hand side. This alpha particle is being released. It's not part of what starts the reaction. It's not going into it. It's coming out of it. What else do we have that's released here? Well, we know if we have a mass number of 226 on the left side, it has to be 226 on the right side. So 4 plus what equals 226? (222). What do we have on the left side for atomic number? 88. What do we have on the right side? 88. 2 plus 86 gives me 88. And if you check your periodic table, which I'd like you to do now, not your chemistry periodic table if you take chemistry 30 right now, but your physics one, just so that you're familiar with the numbers and the placement of things on that one, we would see that atomic number 86 is radon, Rn. Now, something like 90% of isotopes are radioactive. So in all probability, radon-222 is radioactive as well. I know that certain isotopes of radon are certainly radioactive. They occur in the ground. In fact, there's an issue with radon gas seeping into people's basements because it occurs in high concentrations in some places. You got to get it tested and got to get it sealed. And if you have radon gas coming in, because you got these radioactive nuclei that are coming into your basement, which is not good. I'm not sure about this isotope, but in all likelihood, it is radioactive, which means that we're not done. Okay, I mean, we're done this question, but it means that radon or radium-226 has decayed into something, but the chain isn't over. That radon-222 could in turn decay into something else. Yep. Yeah, it could eject another alpha particle, or it could eject a beta particle. You know, whatever the issue is with it that makes it unstable. Too many protons, too many neutrons, whatever. All right, let's write another one here. This one says, write the nuclear equation for the transmutation of radioactive isotope lead-214 undergoing beta decay. By the way, if we don't specify, we mean beta minus. If we mean beta plus, we'll tell you beta positive decay, or positron emission, maybe we'll say. We've got lead-214 undergoing beta negative decay. It's decaying into a beta particle. The beta particle isn't forming part of the parent or the reactants, using chemistry terms. Rather, it's forming part of the right-hand side, what's left over after everything happens. This beta particle, this electron, has been released from the nucleus. What do we have left in the nucleus? Well, you remember that in the nucleus, when a beta particle is released, a neutron changed into a proton and an electron. We have the same number of protons and neutrons combined. 214 gives me 0 plus 214. But remember what we have? One less neutron, one more proton. Minus 1 plus 83 gives me 82. This is bismuth. Here is the most common mistake made in this unit. There are lots of mistakes that people make, but this is the single most common mistake that people make in this unit. People don't write 83 for this. What do you think people would write out of carelessness? 81. Okay, it is not 81. If this was beta plus, beta positive decay, then that would be 81. If it's beta minus, then it's going to be 83. Well, we just assume that it's beta minus here. That's what I meant when I write the question. Really, we should say beta plus or beta minus, but if it doesn't say, you're going to assume beta minus. Now, there is one more thing that happens here. About 80 years ago, it was noticed that there was a little bit of missing energy in this reaction. Something happened. Something's missing. We write this out. Everything balances, but something's missing. So we introduced a new particle to explain the missing energy. We called it an antineutrino. The antineutrino carries off the missing energy. I'm not sure the time frame in which it was observed, but it has since been observed. We know that these antineutrinos actually exist. And we know that every time we have beta negative decay, we have an antineutrino produced. This, by the way, is a symbol for a neutrino. This is the symbol for an antineutrino with a little line over the top of it. That occurs every time we have beta minus decay. Now, on the flip side of that, I'll put a little star by this. Every time we have beta positive decay, what's produced? What do you think is going to be produced here? A neutrino. You don't get either one of them with alpha decay, but with beta minus, you get an antineutrino. With beta plus, you get a neutrino. I don't have a good way to remember that other than tell you the way that I remember it. I mean, I'm bad at remembering things like that. Okay, the way that I remember this is to put two words together. To me, anti kind of reminds me of negative. Not necessarily in this context, just in England, if you're talking about counterclockwise, you say anti-clockwise. Okay, anti means going backwards, negative, right? Anti means negative to me. So I associate antineutrinos with beta negative particles. And therefore, by default, the beta positive has to be associated with neutrinos. Go ahead. I'm not sure. I'm not sure, how that would have ever been measured. I'm not sure. Let's do another one here. The following nuclear reactions, phosphorus 30 goes to sulfur 30 and what? Well, 30 goes to 30 plus 0, 16 plus minus 1, that's a beta particle, right? What else? An antineutrino. An antineutrino. It's not an antineutrino with a vector, it's just an antineutrino. Uranium-238 goes to thorium-234. 234 plus 4 gives me 238. 90 plus 2, what's this going to be? An alpha particle. You might call it a helium nucleus if you want. There's nothing else produced there. Could be gamma, but that would be a separate, like a second step, not part of this reaction. 13 plus 0. 6 plus 1. What's that? It's a positron. What else is produced there? That's going to be a neutrino, right? A neutrino, not an anti-neutrino. Let's give you one more here, okay? One more example, not that one. Okay, this one. This is what we call artificial transmutation. Remember we said radioactivity is one way that elements can transmutate into something else. There's lots of ways. Artificial transmutation is not radioactivity. Okay, we're not undergoing alpha decay here. We're not producing an alpha particle. In fact, we're bombarding nitrogen with an alpha particle. There's nitrogen over there. We're throwing an alpha particle at it. That makes the nitrogen unstable, and it decays into oxygen 17. What else? Well, 14 plus 4 is 18. 17 plus 1 is 18. 7 plus 2 is 9. 8 plus 1 is 9. What do we got there? It's hydrogen. Yeah, it's hydrogen. What else could you say that it is? What's another name for a hydrogen nucleus? Because remember, we're talking about nuclei here, not atoms, right? It's a proton, right? One proton, no neutrons. What about this one? Cadmium 105. That's a beta particle. This beta particle is actually getting absorbed. This is actually not an artificial transmutation. This is a type of radioactivity, but it's a type of radioactivity where the beta particle gets absorbed as opposed to being produced. We call this electron capture. An electron is captured by the nucleus. 105 plus 0 gives me 105. 48 plus minus 1 is 47. Right? 48 minus 1 on the left side. And that, I think that ends up being silver. No antineutrino here, because this is not beta negative decay, even though you see a beta negative particle in there. Here's your homework for tonight. I would like you to do worksheet number 24, please. Worksheet number 24 involves a number of these transmutation equations. There's a bunch of them on that sheet, but they will go pretty quickly for you. You can see how quickly these examples have gone for us, right? There's no calculations other than addition or subtraction. Okay, please do all of them tonight, and we'll check them over tomorrow, and then we'll get as far as we can tomorrow.